Pick up a plastic bottle cap or your phone case and look closely. You will find a continuous, faint seam. That faint line is called a parting line. It is a physical confession, proving exactly how the object was actually made. It is easy to assume an industrial designer simply draws a beautiful 3D shape, and a machine magically materializes it into the real world. Industrial design is the engineering of the massive, rigid steel tool that presses the object into its final form. Drawing a digital model in CAD offers infinite, frictionless freedom, but industrial production introduces brutal, unforgiving physical constraints that immediately shatter that illusion. Most of our manufactured world relies on injection molding. You force molten plastic into a hollow steel box, wait for it to cool, and pull it out. Because of this process, every single curve drawn in a concept sketch is immediately bound by the laws of friction and heat. The very first non-negotiable rule of this manufacturing grammar is the draft angle. In this cross-section of a steel mold and plastic part, walls appear perfectly vertical, but actually taper by 1 degree, allowing the object to slide out. Drawn at 90 degrees, the plastic grips the steel. The part gets stuck, halting the entire production line. An aesthetic preference cannot override physics. The shape you are allowed to have is strictly limited to the shape the mold can successfully release. The grammar demands that the object's walls maintain a uniform thickness from edge to edge. Look at this thermal diagram mapping heat dissipation across uneven geometry. The thicker section retains heat far longer than the thin edges, causing the final product to warp, sink inward, and double the overall manufacturing cost. Then there are undercuts, any lip, hook, or overhang on the design that faces the wrong direction relative to the opening of the mold. An undercut means the object cannot pull straight out. It demands a complete redesign or adding highly complex, failure-prone sliding mechanisms inside the tool itself. And those small circular marks hidden on the underside of products, those are from ejector pins, physically ramming the plastic free from the steel. Leaving manufacturability checks until the end of the process guarantees expensive redesigns and delays. These physical constraints must guide the form from the very first line. This logic of the tool governs every physical medium. Each process imposes its own version of a mold on the final shape. Cast metal parts are bound by the exact same rules of drafts and parting lines. A flat panel of sheet metal is strictly limited by specific bend radii and material tension. Even garments are entirely dictated by the physical width of a fabric roll and the mathematical logic of flat patterns. The method of mass production is never an afterthought. It is an active, silent co-author, shaping the final form from the moment of conception. Masterful designers internalize the grammar of the factory floor so thoroughly that these manufacturing constraints become entirely invisible to the consumer. They can look at the positive shape of an object and simultaneously read the negative space of the steel box it will eventually come from. Correcting a geometry error is cheap when it exists only as a sketch, but the financial penalty is brutal once a toolmaker has already cut into solid steel. True product development requires seeing every angle, calculating every physical limitation, and understanding the manufacturing consequences before anything is built. That level of foresight is exactly why Depix Design Intelligence was built, to provide concept stage clarity, ensuring the mold is mastered well before the metal is ever cut.